Hello everyone, in this video I'm going to be talking about what is a first and a second order splitting patterns are, or another way of saying when do you have a simple doublet, triplet, quartet versus when you're going to have multiptets, and another way of saying multiptets would be like something like in a doublet, a doublet of triplets, and so on. So before I go into a complex example, let me give you a simple example where you see in a simple splitting patterns, and that would be your first order splitting pattern. So let's suppose I have this propane molecule, and if I'm looking at the number of hydrogens here, obviously I got two hydrogens on the middle one here, and I'm only going to be focusing on how they are going to be this splitting with the neighboring hydrogens. So another way of saying we're going to be looking at three bond splittings here, or three bond couplings, you can say. This hydrogens that are in the middle here, they are going to be surrounded by hydrogens that are going to be on the right carbon, and they're also going to be surrounded by, or they're also adjacent to the carbons that are on the left side. So another way of saying the total number of hydrogens that these middle two hydrogens will be adjacent to would be 6. Now, these protons right here, the proton on the left carbon and the proton on the right carbon, they're actually equivalent to one another. There's really not any difference. So as a result, you will very well see a very simple splitting patterns, and we call that in a first order splitting patterns, and where we can just use a rule of n plus 1. So right now I have 6 adjacent protons here, and since you have 6 adjacent hydrogens here, your splitting, or the number of peaks that you would see for these middle two protons, would be a clean septet. So you're gonna see a clean septet. So that's in a first order splitting where you would have this n plus 1 rule being obeyed. And when you go into something a little bit more complex, you may not necessarily have a first order splitting, but rather a second order splitting where the n plus 1 rule doesn't really work that well in terms of determining the number of peaks here. Okay, let's look at this example that I have on the on the left side here. So on this example, I'm going to be focusing on the protons that are going to be actually onto the second carbon from the left. So I have two protons here, and I have a CH3 group on the left side, and I have two protons on the right side. And there is an R group, and we could be careless what that R group could be. Could be an aromatic, or could be, a halogen or something. Like, we could be careless. So what we're really worrying about here is what's going to be the splitting pattern for this middle two protons that we got here, or middle two hydrogens that we have here. And to answer that question, we're going to be looking at how many adjacent protons you're going to have to this particular hydrogen. So obviously, when we're looking at from the left to the right, I'm going to call this to be A, I'm going to be calling these protons to be B, and I'm going to be calling these protons to be C. So when I'm looking at the splitting patterns for the proton B, I know this proton B is going to be coupling with the proton C, because those are the adjacent one, and they're also going to be coupling with proton A. And since they are not really equivalent anymore, so this A and this C, they're not really equivalent anymore, it's not gonna be easy to say that it's gonna be in a first order splitting. A lot of time in a sophomore organic, you would probably say it's a multiptet, but or even you would say, okay, we got 3 protons here, I got 2 here, so that's in a total of 5. Maybe it's gonna be a sextet, but that's not really a wise way of saying it. I'll tell you when you could possibly have a clean sextet here, but before we do that, I'm gonna tell you how this is really not in a first order splitting, but rather it's in a second order splitting, and that's because you're gonna have a different proton on A that's in a different environment, and then you're gonna have a different protons that's on the C that's in a different environment coupling with B. Now, the coupling constant that's going to be, so this is a 3-bond coupling constant between A and B, and then you have a 3-bond coupling constant between B and C. Now that may not very well be equal. So let's suppose if it is an equal, then maybe we can just look at, okay, it's going to be in a first order splitting, and we will say it's going to follow this n+1 rule, because it's just gonna overlap with it. So then maybe you would see in a sextet here because you have a 5 number of protons here. But then, ideally speaking, this may not very well be equal to one another. So this, I would say, is really not equal to one another. And in that case, um, this is going to be in a second order splitting, and it's not really going to be a clean sextet, or another way of saying it's not really going to have 6 peaks in there, even though even in the previous one it's not really 6 peaks in there, but those peaks actually overlap from the second order spectrum because the coupling constants are the same, and it looks like it's a clean sextet or it's in a clean 6 peaks in there, but it's not really clean 6 peaks even in that particular case. And sometimes that would happen if you're using a very low range NMR instrument, maybe like in a 60 megahertz or maybe 100 megahertz or even up to 4 megahertz, you may not be able to see those clean splittings in there, and you may see just a clean sextet here or 6 peaks in there. But if you use something like a higher order NMR, maybe 500 megahertz or something like that, then you may start seeing the peaks for different peaks for the left proton and the right proton, and that's when you start seeing this second order spectrum. So it's not really going to be a clean sextet at that time. Now, let's look at how it's going to be shown up on the NMR if it is not coming out to be in a first order splitting here, but rather it's in a second order. And remember, the second order would happen obviously whenever the coupling constant is not going to be the same between the A and B and between the B and C. And here we're only focusing on the B for right now. So in case of B, so when B couples with A, since it's coupling with these 3 protons here, so I can probably just use an n+1 rule here, and I would say it's going to be and a quartet due to the one on the right, on the left side. And then I can also use an n+1 rule for the C protons. And for those ones, I can probably just write down n+1 since we already used n here. That's going to be, since you have 2 protons, so that's going to be a clean triplet. So you would see either a quartet of triplet or you would see a triplet of quartet. Now, how does that really look like in terms of a tree diagram? So let's see, we're gonna have this splitting, and suppose for first time it comes out to be a quartet of triplet, so maybe a QT, and you could very well have a T of Q quartet of triplet, or maybe a triplet quartet. That really depends on whichever coupling constant is bigger that comes first. So let's suppose if the coupling constant is between AB is bigger than the BC, so it's still in a 3-bond coupling here, then I'm going to say the AB would come up first. So that's going to be a quartet due to the AB here. And we're going to call that a quartet of triplet in that case. And then the opposite would be true if your coupling constant between the AB is actually smaller than the coupling constant between BC. So in that case, then you would have this C being shown first, and that would be a triplet first, and then after the triplet you would have a quartet. So that's how you know whether you're going to be seeing a quartet of triplet or a triplet of quartet. It really depends on whichever coupling constant is actually bigger. So let's suppose if I'm focusing on how would the QT look like, or the quartet of triplet look like, and I can start using this as my example here. Suppose I have, so gonna go ahead and draw 3 of those because it's a quartet, so I want to draw actually 4 first. So I'm trying to make sure that space is as equal as possible. So I'm starting out with this HB proton, and due to the HB proton, and these are going to be your HA, so you have 3 of those. So because of the 3, you're going to be seeing the 4 splittings there. So you're going to have the distance between those 4 here. That's going to be your coupling constant. Maybe I can change the color on this here. So right there, even right there, those are going to be your couplings constants. So from here to here, from here to here, from here to here. So those are going to be the coupling constants between A and B. So it's a 3-bond coupling. And then further down, this 4 is going to split again into the 3, or it's going to be in a triplet. So every single one of those will be shown up as in a triplet. So it gets a little bit complicated here. And now we're going to be taking the next set of coupling constants to be a little bit smaller. So that's why you would see the Q, the quartet first, and then you will see the triplet afterward. And I can go ahead and draw those out right here. And there's a good chance that they may very well overlap with one another. I'm just going to go ahead and draw a big line here. And since they will be overlapping, another way of saying every one of those will be showing up 3 signals. So something like that. That's 3 signals from this left one. And then I would have 3 signals from the next one, something like this. So their coupling constant needs to be the same. And then I would have a next set of signals from the third one here. And then I would have the next set of signal from this last one here. So I'm just taking that the second coupling constant is significantly small, so that's why those lines are very close to one another. But then if, there's a good chance that their coupling constant is not as small as I have made here, these lines may overlap. So another way of saying the splitting or the triplet of this and the triplet of that, they may overlap with one another. And you would have a triplet, maybe one of the lines right here for that one, and the triplet, one of the lines would be right here. So they could very well overlap. And then obviously you're going to have these lines right there. Those are going to be the coupling constants between the B and C. So this is how you're going to be drawing a quartet of triplet. But at the end of the day, if I want to count how many peaks I really got here, and starting from the left to the right, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you actually have a total of 12 peaks in this particular one. And if that's in a second order spectrum, and that in second order spectrum you'd see 12 peaks in there. And what we have said earlier, that if the coupling constant that's between the BC and the AB is roughly the same, then you might just come down to in a first order spectrum, and that 12 peaks will turn on into a clean sextet. So it's not even really a clean sextet, but they would overlap where you would see only 6 peaks in that particular case. So that would be your quartet of triplet in this particular case. But then what if in a second case scenario where your the coupling constant for the BC is actually bigger than the coupling constant of AB, then you would be seeing in a triplet of quartet. So how would the tree diagram for a triplet of quartet look like? So I'm gonna go ahead and first of all draw a triplet, and I'm just gonna use these guys right there. that's one, that's two, and I need another one, and that's gonna be, so first you want to draw a triplet. So this is what your triplet gonna be. So obviously starting from an HB, this is gonna be your HC proton. Remember that was on the bottom was an HC here. So you see in a triplet first, and even on that triplet, the distance between those lines right there would be, so right here and right here and right here and right here, those would be your coupling constants between B and C. So that's a 3-bond coupling constant. Now, the second set is supposed to be smaller, and when I'm drawing the second set here, and I can probably just use in a different color here. So maybe I can just go ahead and draw a straight line first. And each of those splittings that you have here, that was the triplet, they're going to split further down into a quartet. So that's what triplet of quartet really means. So every one of those I would have maybe 4 lines now. So because of this first signal right here, I should see a clean quartet. So you have the triplet first, and I'm going to see a quartet because of each of these lines. So maybe let me draw a quartet or 4 lines that are kind of equally spaced from one another, and then I'm just going to copy those down. So hopefully they are as equal as I could get him. So I'm just going to go ahead and duplicate those, and I'll use them a little bit. So that would be actually right here. Okay, so that was because of this first proton, and now because of this second proton, or the one in the middle, I'm going to be seeing the splitting again, and I can go and change the color on this, and that would be right here. Now you can start seeing how they're actually overlapping with one another, but then you would still see, 4 signals there, or 4 peaks rather, not want to call signals. And then I would see another set here because of the third one. So I want to keep that in the middle right here. So then you're going to have another 4 signals there. So the distance between the first 2, you can use that distance to actually figure out the coupling between the A and B in this case. And obviously, remember the AB coupling constant is actually smaller in this particular case. So like I have said in the previous case, I didn't really overlap those, but then I did mention that they could overlap with one another, and that's what makes it so difficult when you're looking at these tree diagrams. But at the end of the day, when you counting how many peaks you really got here, it's still going to be 12 peaks. So that doesn't really change. It's just how it really looks like may change whether you're dealing with something like a quartet of triplet or a triplet of quartet. And those 12 peaks will be turning into a sextet if your coupling constant between those two guys were actually the same. So that would have been a first order splitting. But since it's unlikely to see these coupling constants to be the same, and that's why you're going to be seeing these 12 peaks. So a lot of time the teachers ask you like how many peaks you're really going to see on this signal B. Then you can always use this formula where you say it's going to be n plus 1 times n plus 1. So because of n plus 1, we had gotten the quartet, which means the 4 peaks. And because of the n plus 1 right here, we have gotten the triplet, that means 3 peaks. So 4 times 3 is going to be 12. So you will get a 12 peaks. Now, whether you would have actually a quartet of triplet or a triplet of quartet, that's in a different story. Then you really got to look at which particular coupling constant is bigger, and you call that first, and then the smaller coupling constant comes afterward. But the number of peaks, regardless whether it's in a quartet of triplet or a triplet of quartet, will still be the same. And remember, um, typically we call those as a multiptet because it's just so hard to kind of decode those, and especially sometimes in sophomore organic chemistry, they don't bother kind of trying to figure out the coupling constants too much. But every now and then you may see run into a scenario where you're actually worrying about the coupling constants and worrying about the number of peaks in this particular case. So You would call those a clean sextet if the coupling constants were the same. You would call those multiptet a lot of times because they are being coupled with different types of protons, but the actual name for the multiptets would be either a quartet of triplet or a triplet of quartet. So this is how you're really going to be looking at your first or second order splitting patterns. If you have any questions, feel free to leave any comments in the section below.